Hello and welcome to my presentation about spiking neural network decision feedback equalization for IMDD systems. My name is Alexander van Bank and this is a joint work by me and my colleagues Eike Manuel Edelmann and Laurent Schmal. So about the motivation, we looked at the scenario of an IMDD optical link with chromatic dispersion. And this chromatic dispersion induces inter-symbol interference, and this inter-symbol interference interferes with our communication. It decreases the bit error rate, so we need an equalizer to compensate this at the receiver. And it has been shown that machine learning can actually improve the equalization for these type of systems. But we have this trade-off between computational complexity and performance. Currently, most equalizers are implemented on digital electronics, and the problem is that there's this digital CPU efficiency wall, which is mainly because of the size of the transistors can get too small, because you get problems of dead silicon, because the heat dissipation is too much. You can't get the heat off the chip. So we need some different systems, not for Neumann architectures, right? So there are then possibilities for like neuromorphic hardware, right? And there are different possibilities to do that, like photonic and electronic neuromorphic hardware, where you can get beyond this digital CPU efficiency wall. And now the question arises, how do you implement an equalizer on neuromorphic electronics? And this question we want to tackle here. So first of all, about the setup, we map random bit sequences to 4 palm symbols. We upsample them, pulse from them, then the chromatic dispersion, nonlinear detector and the noise comes into play, and out of this measured signal then we want to estimate the transmitted symbols at the receiver. Currently this is done with this equalizer and demapper block here, and we try to replace him with neuromorphic equalizer and demapper. And spiking neural networks, they are a promising candidate to be implemented on neuromorphic hardware, and they enable energy efficient computing. So what are spiking neural networks? Spiking neural networks are interconnected neurons with adjustable, so trainable weights. And these interconnected neurons are basically the same principle as in artificial neural networks, right? You have these connections, you have the neurons, but the difference here is that we replace the neurons. So we don't pick tangent hyperbolicus or rectified linear units or something like that. We replace them with these special kind of neurons that try to mimic the behavior of the human brain. Since the human brain is quite an efficient machine. How does it work? It exchanges discrete events, so-called spikes. These neurons have then an internal state, the so-called membrane potential. And if an input spike, so one of these discrete events arrives, it starts in synaptic input current. And this synaptic input current then charges the membrane potential, and if this membrane potential then exceeds a certain threshold, a spike is emitted, sent to the next neurons, either via the lateral or the feed-forward connections you can see above here, and then via the feed-forward connections the spikes can be sent to the next layer, or via the lateral connections they can be sent to the neurons inside the same layer. And how does this look in time domain? So if there's an input spike here in purple, it starts this input charging current in yellow, and this current then falls exponentially and it starts charging the membrane potential, so the internal state. And if more spikes are coming more closer, more dense in time, then the membrane potential, which also leaks in time, can rise to higher values. and if they are sufficiently dense, either in spatial, like down here, or in time, if they are sufficiently many spikes in a certain time, then the membrane potential is loaded towards this threshold here, and a spike in blue is emitted, and afterwards the membrane potential falls down to the initial value again. Okay, so we talked about spikes, but obviously we have real valued inputs, and that's the problem that so-called encoding handles, right? It converts real value data into spike signals, and this is the communication interface to the neuromorphic hardware. And we propose this so-called ternary encoding, which basically quantizes the absolute of the input value, and then the resulting bits, spikes, are then signed according to the input value. So if we have like a 0, it would be all 0. If we would have the largest possible absolute, it would be all 1s, right? And then if it's the largest absolute but negative sign, it would be all -1s. And these bits or trits, right, we place them then in the first time step of the processing of the estimation, right? And afterwards we leave trailing zeros, so the neurons, when they fire, they can send their spikes to the neurons in the upstream layers or in the same layer, and communicate amongst and evolve over time. So we now have this encoding, and we have this green block of neuromorphic equalizer and demapper. But what's inside this block? So this block actually consists of this structure above, where you can see it looks quite similar to a classical decision feedback equalizer. The difference, however, is that we first have this encoding, and then the feed forward tap delay line, which contains the input received values, which are then fed to the spiking neural network. The spiking neural network will then estimate a class of the received, the transmit symbol class, and this transmit symbol class is then one hot encoded, placed at the first time instance with trailing zeros as for the encoding above, and also feed to this tap delay line structure, and then to the spiking neural network. And we mentioned the time, and so what's about the time? We have this channel time, right? So if a channel clock, and if on each instance where a transmit symbol is received, we would then have to reset the spiking neural network, make all this encoding, so the ternary encoding, quantize the absolute, sign them, place the previously decided class symbols, one hot encoded at the first time instance, trailing zeros, and process it for a time t max. And the output layer, so the last layer of the spiking neural network, these neurons don't emit spikes, so they don't reset themselves. They just integrate all the incoming spikes over time, and their membrane potential then rises with each incoming spike. And at the end of Tmax, you look for the neuron with the highest membrane potential. This is then your class estimate. Okay, so about the channels, we compared ourselves to the paper of Arnold et al. And therefore the first channel we use, channel A, is the channel they use the paper, which has then an equalizer tap count of 17. And channel B is then a more standard single mode fiber channel case with 50 gigabaud and a resulting equalizer tap count of 41, since the significant the amount of significant channel taps would also be 41. And we used 8 trits for encoding, so quantize the absolute by 8 bits, then sign them according to the input value sign, we implemented it using Norse, which is a PyTorch based library for spiking neural networks. And we used 5 epochs, 2000 batches with a huge batch size, so we could be sure that the spiking neural network, or generally the equalizers, converged. And we used standard learning rates and cross entropy loss since we trained these classes. Okay, so about the references. We compared ourselves to a linear equalizer, linear minimum mean square error equalizer, which is then actually just a feed forward path and a linear layer, afterwards the decider and a bitmapper. We furthermore compared against the classical decision feedback equalizer, which has then this feed forward structure and also the feedback line below. And you can see that the classical decision feedback equalizer didn't brought that much of a gain here for the channel A. And we also implemented the ANN equalizer and demapper that was also used as a reference in the paper of Arnold et al. And it consists out of this feed forward line, which is then feed to the artificial neural network, which then decides for a symbol class, which is then also bitmap. And the result of the Arnold et al. Paper is here, and we also trained it with our with many batches, huge batch size, and we could gain quite some performance gain here. The ANN equalizer and demapper with decision feedback structure can be seen here with these straight line and the balls, and it also has these feed forward, feed back line, and an ANN, which then produces out of the previous decisions and the currently received values in class estimate. And there's not that much of a gain, but still a slight gain in BR performance here between the ANN and the decision feedback ANN. And spiking neural network decision feedback equalizer of Arnold et al. Can be seen here in this dashed purple line and dashed purple line with the pluses. And the two curves you can see here are ones for the paper values of Arnold et al. And also the same equalizer trained with these enormous batch sizes. And it performs like or quite similar to the artificial neural network equalizer. So about the SNN DFE we proposed, you can see here that it performs best, but only slightly better than the ANN DFE. So this was the channel of the paper of Arnold et al. And now we look for the more standard single mode fiber compliant channel, the channel B. And we can see here that the ANN DFE outperforms the ANN, but more significantly here. And we can see that the spiking neural network decision feedback equalizer outperforms the spiking neural network. But we can furthermore see that the spiking neural network decision feedback equalizer outperforms the ANN decision feedback equalizer. Okay, and now another point, we also try to train expert networks, right? So we try to train spiking neural networks that operate at a single SNR point, and if the SNR changes, you would have to use the different spiking neural networks. But it turned out that actually training a spiking neural network at an optimal training point, which was in this case 17 dB, outperforms this expert network. So using the generalization of the neural networks, which were trained at an optimal point, works better than just training at all single SNR points and then later on use them in the same region. And this enhancement can be more clearly seen with decision feedback structures. This can be seen here since it starts deviating from the 70 dB line up to 19 dB up to 23 dB. now about the conclusion. The spiking neural network decision feedback equalizer for IMDD channels has better or similar performance than the benchmarks, while promising energy efficient computing. Decision feedback helps against chromatic dispersion, and gain grows with increasing chromatic dispersion in low symbol error rates regions, since the decision feedback structure, as for the classical decision feedback equalizer, imposes the problem of error propagation. So we need low symbol error rates but severe distortions. In this region the highest gain can be seen. And furthermore, we can state that seeking an optimal training point is advantageous compared to just training many spiking neural networks at the SNR points where they will be later on operated. As an outlook, we want to find some better training tools for spiking neural networks, since training spiking neural network is currently still a bit tricky. And furthermore, we want to dive into different communication aspects and want to impose spiking neural networks also there, since they are a key enabler for energy efficient communication. And yes, therefore we try to find ways to implement them in different regions, right? So this concludes my presentation, and thank you for your attention.